Welcome you all to the fluid power system. This is module 2, lecture series 8. The topic is accumulator. Accumulator, it is a device used for storing the pressure energy of the liquid. Okay. See, hydraulic accumulator, it is a device, it stores the potential energy or pressure energy of an incompressible fluid held under pressure by an external source. The stored potential energy is the stored potential energy in the accumulator is a quick secondary source of fluid power capable of doing useful work. See, the hydraulic accumulator, its action is just similar to the storage battery. The energy stored can be supplied at any point of time when required, either suddenly or intermittently. By this way, the accumulators do. This is the hydraulic accumulator symbolic representation of accumulator. Now we'll move on to classification of hydraulic accumulators. See, in hydraulic accumulators mainly three types: weight loaded or gravity accumulator. Second is spring loaded accumulator. Third is gas loaded accumulator. In gas loaded accumulator, two sub classification. First one is non-separator type gas loaded accumulator and separator type gas loaded accumulator. And in subtype B, in separator type, again three sub classifications: piston type separator gas loaded accumulator, diaphragm type separator gas loaded accumulator, and bladder type separator gas loaded accumulator. These are the broad classification of hydraulic accumulators. First one, weight loaded or gravity accumulator. See, it is a vertical cylinder, means it is mounted in the vertical position with a large weight. You can see the diagram. See here, when the hydraulic fluid is pumped into it through inlet valve. See, here is the inlet and here is the outlet. You can see inlet from here, outlet goes here. This is from pump and this is towards actuator. Okay. When the hydraulic fluid is pumped into it, the weight is raised. Because of fluid pressure, the weight is raised. The weight applies a force on the piston that generates a pressure on the fluid side of piston. The advantage of this type of accumulator over other types is it applies a constant pressure on the fluid throughout its range of motion. So, its advantage is it applies constant pressure throughout its range of motion. The main disadvantage of its weight loaded accumulator is extremely large size and heavy weight. It has extremely large size and heavy weight. These two are the disadvantages of weight loaded accumulator, and this makes it unsuitable for mobile applications. Because of these two reasons, this is not suitable for mobile applications. Once we go through the operation, see in this configuration, inside and outside, inlet and outlet. See, in inlet what will happen? The pump output comes to inlet and the pressurized fluid acts on the piston. The piston is travels up against the weight. So because of this external source means weight, because of weight, the pressurized liquid is stored in the cylinder chamber or this accumulator chamber in this yellow colored. Yellow colored is accumulator chamber. Here the liquid is stored with pressure energy, and the outlet valve is blocked. So wherever it required in the sudden manner or intermittently, it can be used according to its application. Okay. See, in the beginning, what will happen? The ram is at the lowermost position. The ram is at this is sliding ram, and this is a fixed cylinder. So once we go for a construction, it consists of a vertical cylinder which is fixed in position. See this one. This is fixed in position. This is a cylinder fixed in position. The cylinder is provided with inlet and outlet. The cylinder, see, look at here, this is the inlet and this is the outlet. This is outlet and this is inlet. Okay. A ram is fitted in the cylinder which carries heavy weight. See, this is the ram, this one is a ram, and with a load means weight. Okay. On its top, and it is capable of sliding up and down inside the cylinder. See, this sliding ram will move up and down inside the cylinder. This is the construction of simple hydraulic actuator like weight loaded. See, at the beginning, the ram is at the lowermost position when the pump starts supplying high pressure liquid, and this is not used by an hydraulic system. Okay, then the high pressure liquid will lift the ram and high pressure liquid is stored in the cylinder. When the ram is at uppermost position, the cylinder is full of high pressure liquid, and accumulator stores the maximum pressure energy. When the hydraulic system requires a large amount of pressure energy, the accumulator starts supplying the same and the ram moves down. So here we can conclude that the accumulator supplies the pressure energy either suddenly or intermittently. Second type accumulator, spring loaded accumulator. Once go through the diagram. See, when I go for a construction purpose. The construction of spring loaded accumulator is shown in this figure. In this figure mainly consists of piston rod and piston rod or plunger, then cylinder body and movable piston. See, this piston is movable. This one is movable piston and a compression spring. See, this is the movable piston. This one is movable piston, and this is a spring. It can be compressed and expandable. Okay. Here oil is stored in the ram against the preloaded spring. See, here the liquid is stored against this spring force. Okay. This is the construction purpose. When we go for a operation, see, as the fluid enters the accumulator, the spring is compressed by the hydraulic fluid. The pressure in the accumulator depends on the size of the cylinder and preloading of the spring. In the accumulator, oil pressure increases as the spring gets compressed. When the fluid is discharged from the accumulator, it causes the spring to expand. As the spring approaches its free length, the accumulator pressure drops to a minimum. Thus, the pressure exerted by the spring loaded type accumulator on the fluid is not constant as in the dead weight type. Okay. And the advantages of spring loaded accumulator here is they are easy to maintain, they are suitable for low pressure applications, they are less expensive compared to weight loaded accumulators, and it has some limitations. Here mainly pressure exerted on the fluid is not constant. They deliver a small volume at low pressures. These are the few of the disadvantages about spring-loaded accumulators. Third type accumulator, that is gas loaded accumulator. As the name implies, here the fluid energy, the pressure energy is stored against the gas load. These are also called as hydropneumatic accumulators because gas is used. The compressibility of gases accounts for the storage of potential energy. Okay, and the principle of working here is it works on the principle of Boyle's law. It states that for a constant temperature process, the pressure of a gas varies inversely with its volume. When the gas is compressed to half of its original volume, the pressure of the gas increases to 2 times of its initial pressure. The compressibility of gases accounts for the storage of the potential energy. This energy forces the oil out of the accumulator when the gas expands due to the reduction of system pressure or when the fluid is supplied to the machinery or system. Here mainly two types of gas loaded accumulator, non-separator type and separator type. First we will move on to non-separator type accumulator. Look at the diagram. This diagram shows non-separator type gas loaded accumulator. See, in this type, the gas which provides the load is in direct contact with the hydraulic fluid. In this case, oil and gas are not separated, hence they are always placed in vertical position and there is a direct contact between oil and gas. Okay, hence it is a non-separator type accumulator. And one more diagram for non-separator type gas loaded accumulator. See, here is the liquid side and here is the gas side. Here there is a to supply one valve is there to supply gas and to supply fluid. Here only inlet and out. This same port acts as an inlet and outlet for the fluid. Okay. Here it is a non-separator type accumulator. In separator type accumulator, see, in separator type accumulator, the both gas and liquid are separated by an element. See, depending upon the separating element, separator gas loaded accumulators can be classified as piston type gas loaded accumulator, diaphragm type gas loaded accumulator, and gas bladder type gas loaded accumulator. Okay, first we will move on to piston type gas loaded accumulator. Okay, look at this diagram. The construction of the piston type separator type gas loaded accumulator. Here it consists of cylinder body, piston and a recharge valve and hydraulic fittings for inlet and outlet. Okay. In operation, what will happen? The pressurized gas is introduced into the cylinder through gas valve. When the system requirement is low or system is idle, oil will enter into the accumulator through inlet outlet oil port. This one, the inlet outlet oil port. As the piston pushes the gas, the volume of gas decreases and the pressure increases as per the Boyle's law. This gas pressure is used as a potential energy to force the oil out when it is required by the system or circuit or machinery. Okay. Next we will move on to second type. Here see, this is also one of the diagram. It is a metal bellows type accumulator. Second and third types are diaphragm type and gas bladder type accumulator. First we will move on to diaphragm type gas loaded accumulator. We will move to the construction and diagram. See here the diagram, it shows diaphragm type gas loaded accumulator. When we go for a construction, it consists of a spherical body. Here the spherical body inside it, and flexible diaphragm. The spherical vessel is separated into two compartments by a flexible diaphragm. This is the flexible diaphragm. See this one. One compartment is connected to the hydraulic system and other is connected to the high pressure gas system. See here, this is for a gas, high pressure gas, and this is for hydraulic system. Thus the diaphragm serves as an elastic barrier between the oil and gas, and it is a separator type, and the both gas and liquid both are separated by a this flexible diaphragm. And operation is, see, in most of the design, spring loaded, normally open check valve or screen is provided at the liquid connection to prevent extrusion of the diaphragm into the oil line when the fluid is discharged. When the oil is delivered into the accumulator, it deforms the diaphragm. The gas is compressed when the charged oil pushes the diaphragm against it. This gas pressure is used as the potential energy to force the oil out when it is required in the circuit. See, look at here, there are two chambers. See here, this yellow colored is liquid one, this blue colored is gas chamber. When the liquid, pressurized liquid comes and acts on this flexible diaphragm, and this gas is compressed. This gas is compressed, so pressure energy is created. So when this liquid is comes and pushes this diaphragm move up, and the gas gets compressed, and the pressurized liquid is stored inside it. Wherever the fluid requires, because this gas force is utilized to push out the liquid immediately or intermittently. Next we will move on to gas bladder type accumulator. Here the gas bladder accumulator, you can see it. When we go for a construction, it consists of a bag or bladder made up of synthetic material that can be installed or removed through the shell opening at the poppet valve. The poppet valve closes the inlet when the bladder is charged fully. Okay. And when we go for a operation, see, the hydraulic pump delivers oil to the accumulator. The bladder gets deformed as the oil enters to the accumulator, and volume of gas decreases and pressure of the gas increases. Thus, hydraulic energy is stored indirectly, compressing the gas in the gas bladder by oil. When the additional oil is required by the system or machinery, it comes from the accumulator due to the pressure drop in the system. See, here there is a chamber provided. There is a chamber provided for the, see, here there is a chamber provided for this. This is a chamber provided to store the pressurized liquid, and here is the gas chamber. So when pressurized liquid comes and fills the space and pushes this chamber, nitrogen gas chamber, so the bladder gets compressed, and the stored energy, when the potential energy of the liquid is stored inside the accumulator chamber. As the requirement of fluid comes from the machinery or circuit, the nitrogen gas gets expanded because of pressure drop in the system. Because of this expansion pressure will helpful to push the liquid to the hydraulic system. By this way, the gas loaded type separator, gas loaded type accumulator is works. Okay. Symbols of accumulator. Diagram 1 indicates simple type of accumulator. There is no any barriers. Okay, simple type of accumulator. And second diagram shows gas loaded accumulator. See, in this gas loaded accumulator, this is a inverted empty triangle. It indicates gas loaded. Okay, and third is spring loaded accumulator, and fourth is weight loaded accumulator. These are the graphical symbols of different types of accumulators. This is important section, numericals on cylinders and motors, numericals on linear actuators and rotary actuators. Next is formula to be remembered. You can see the difference between pumps and actuators. See here, not much difference in case of basic formulas like theoretical torque, theoretical power and actual power, and theoretical flow rate. These equations are almost all same. You can see here, theoretical torque equal to P into Vd dividing by 2 pi, and in case of actuators, theoretical torque equal to P into Vd dividing by 2 pi. For these two cases, no issue. All these two equations are same. And when you go for a theoretical power, theoretical power equal to theoretical torque into angular velocity. Here also same. Theoretical power equal to theoretical torque into angular velocity, that is omega. And when you go for actual power, in the place of theoretical there is a actual. Actual power equal to actual torque into angular velocity. In case of actuators, actual power equal to actual torque into angular velocity. There is no difference in these equations. When you go for a theoretical flow rate or a theoretical discharge, Qt equal to Vd into N, volumetric displacement into speed. Here also in case of actuators, the equation is same, no doubt in it. Okay. When we go for a volumetric efficiency, in case of pumps, volumetric efficiency equal to actual flow rate divided by theoretical flow rate. Now come to the actuator case. See, volumetric efficiency is reciprocal of volumetric efficiency of the pump. Here volumetric efficiency equal to theoretical flow rate dividing by actual flow rate. Look at the comparison. Numerator and denominator maybe. Here in pumps, actual flow rate is numerator, theoretical flow rate is denominator. Here is the ulta in case of actuators. You can see the difference in case of volumetric efficiency. Similarly for mechanical efficiency also, when we express the mechanical efficiency in terms of torque, look at here the difference, numerator and denominator. In case of pump, theoretical torque dividing by actual torque. In case of actuator, mechanical efficiency is actual torque divided by theoretical torque. Okay, you can see the difference. Next is one more formula for mechanical efficiency. Here PQT dividing by omega TA means pressure into theoretical flow rate dividing by angular velocity into actual torque. In case of actuators, mechanical efficiency equal to angular velocity into actual torque divided by pressure into theoretical discharge. So numerator and denominator here is reciprocated. And last is overall efficiency. Here overall efficiency is for both cases. It is the multiplication of mechanical efficiency and volumetric efficiency. When we go for one more formula, here numerator and denominator here is reciprocated. You can see the difference here. In case of pump, overall efficiency equal to pressure into actual flow rate dividing by angular velocity into actual torque. In case of actuator, angular velocity into actual torque dividing by pressure into actual flow rate. This is the comparisons or what we call difference between the formulas in case of pumps and actuators. Take one numerical. A hydraulic motor has a displacement of 165 centimeter cube and operates with a pressure of 70 bars and a speed of 2000 rpm. If the actual flow rate consumed by the motor is 6 liter per second and the actual torque delivered by the motor is 170 Newton meter, find volumetric efficiency, mechanical efficiency, overall efficiency and actual power delivered by motor. Okay. First note down the data given in the numerical. Here VD volumetric displacement 165 centimeter cube, 165 into 10 to the power of minus 6 meter cube. Next pressure is 70 bars, 70 into 10 to the power of 5 Newton per meter square, and speed is 2000 rpm, and actual flow rate QA is 6 liter per second, that is 6 into 10 to the power of minus 3, that is 0.006 meter cube per second. Next is actual torque TA equal to 170 Newton per meter. Now we will move on to find out unknown things: volumetric efficiency, mechanical efficiency, overall efficiency and actual power. We'll move on to first case, volumetric efficiency. There is a formula: volumetric efficiency equal to theoretical discharge dividing by actual discharge. Here to find out theoretical discharge, there is a formula: volumetric displacement into speed dividing by 60. So VD is given and N is given as a data. Just substitute the values in this equation. QT equal to VD is 165 into 10 to the power of minus 6 into speed is 2000 dividing by 60. We will get QT as 0.0055 meter cube per second. Okay. Once we got QT, next QA is already given in the data. So both values we got. So we can easily find out volumetric efficiency here. Volumetric efficiency equal to theoretical flow rate. Just we got the answer, that is 0.0055 dividing by QA, actual flow rate, that is 0.006. So simplify this, we will get 91.66% as volumetric efficiency. So sub question A, volumetric efficiency equal to 91.66%. And second sub question, that is mechanical efficiency. Here in terms of torque, mechanical efficiency equal to actual torque dividing by theoretical torque. Actual torque is already given as a data. Next theoretical torque is unknown. So find out theoretical torque. There is a formula: theoretical torque equal to pressure into volumetric displacement dividing by 2 pi. PE and VD both are given as a data. Substitute the values in this equation. It becomes 70 into 10 to the power of 5 into 165 into 10 to the power of minus 6 dividing by 2 pi. Simplify this, we will get theoretical torque as 183.829 Newton meter. Now both values we got. Actual torque already we have, and just theoretical torque just we got. Substitute these values in the mechanical equation. So mechanical equation equal to mechanical efficiency equal to actual torque, that is 170 dividing by theoretical torque, that is 183.829. Simplify this, we will get 92.477%. The sub question B, mechanical efficiency is 92.477%. Next we will move on to overall efficiency. Overall efficiency formula is multiplication of mechanical efficiency and volumetric efficiency. Mechanical efficiency is 92.477% into volumetric efficiency is 91.66%. Simplify this, we will get 84.76%. Sub-question 3, sub-question C, overall efficiency is 84.76%. And last sub-question, that is actual power delivered by motor. Here actual power, we have a equation, actual power equal to theoretical torque into angular velocity. Here angular velocity formula is 2 pi n dividing by 60. Actual torque we have n, we have, substitute the values in this equation. 2 pi into n is 2000 into actual torque, that is 170 dividing by 60. So we will get 35,600 watt. Here when we converted into kilowatts, the actual power delivered by motor PA equal to 35.6 kilowatt. Sub-question D, actual power delivered by motor PA is 35.6 kilowatt. Next we will move on to another question. The pressure rating of the components in a hydraulic system is 10 to the power of 5 kilopascal. The system contains a hydraulic motor to turn a 0.3 meter radius drum at 30 rpm to lift a weight of load 4000 Newton as shown in figure. Determine the flow rate and brake power if the motor efficiency is 100%. Look at the diagram. In the diagram we can see the load, then diameter of radius of the drum, okay, load, okay. Then first note down what are the things to be find out. VD to be find out, volumetric displacement, and P is given as a data. 10 to the power of 5 kilo means again 10 to the power of 3 will be added. It will become 10 to the power of 8 Pascal or 10 to the power of 8 Newton per meter square. Now we will move on to find out theoretical torque. To find out theoretical torque, there is a formula. TT, theoretical torque, equal to pressure into volumetric displacement dividing by 2 pi. So here TT is nothing but a force into distance. Torque means force into distance. Force is given as a data, that is 4000 Newton, and radius is given, that is nothing but a distance, that is 0.3 meter. So theoretical torque equal to 4000 into 0.3 equal to P is 10 to the power of 8 into VD is unknown, we have to find out, dividing by 2 pi. Simplify this equation, we will get VD as volumetric displacement as 7.54 into 10 to the power of minus 5 meter cube per revolution. Next we will move on to theoretical flow rate. To find out theoretical flow rate, there is a formula QT equal to VD into N dividing by 60. N is already in the question itself, and VD just we got, substitute the value in here, that is VD is 7.54 into 10 to the power of minus 5 and into N is 30 rpm dividing by 60. QT is 0.0000377 meter cube per second. And next unknown thing is brake power. Here to find out brake power, pressure equal to, power equal to pressure into what we call theoretical flow rate. P is in our hand and QT is also in our hand. Substitute both and we will get, when we simplify this, we will get the answer for brake power. P is 10 to the power of 8 into QT is 0.0000377. Simplify this, we will get 3770 watts. When we convert this into kilowatt, that is 3.77 kilowatt. So the answers of this question is flow rate, theoretical flow rate, that is 0.0000377 meter cube per second, and the brake power is 3.77 kilowatt. One more numerical. A hydrostatic transmission operating at 105 bar pressure has the following characteristics. The table has given left one is pump and right one is motor. In case of pump, Vd equal to 100 centimeter cube, volumetric efficiency equal to 85%, mechanical efficiency equal to 90%, speed equal to 1000 rpm. When we go for a motor, Vd is question mark, volumetric efficiency equal to 94%, mechanical efficiency equal to 92%, and speed is 600 rpm. Find the subquestion A, displacement of motor, and B, subquestion B, motor output torque. Now we will move on to the solution part. Here first one is displacement of motor. See, in the question it is about both pump and pump and motor. First we will move on to find out pump case. Theoretical discharge for pump equal to volumetric displacement into speed dividing by 60. Both Vd and speed both are given as a data. Substitute the values in this equation, that is 100 into 10 to the power of minus 6 into 1000 dividing by 60. We will get theoretical flow rate for pump is 1.667 into 10 to the power of minus 3 meter cube per second. Next is actual flow rate. Actual flow rate here, actual flow rate of the pump equal to volumetric efficiency into theoretical flow rate of the pump. So theoretical flow rate of the pump, the answer is in our hand. Just substitute the value, and volumetric efficiency is given as a data, that is 0.85. Simplify this, we will get the actual flow rate of the pump is 1.42 into 10 to the power of minus 3 meter cube per second. Now we'll move on to the motor end. The actual flow rate of the pump is the actual flow rate of the actual flow rate to the motor. So for the motor, the actual flow rate of the motor is nothing but a actual flow rate from the pump, that is equal to 1.42 into 10 to the power of minus 3 meter cube per second. So once we got actual flow rate for motor, we can easily find out actual theoretical flow rate for the motor. Here theoretical flow rate of the motor equal to volumetric efficiency into actual flow rate of the motor. Substitute the values. Volumetric efficiency given as a data, and QA just we got. Volumetric efficiency is 94% and actual flow rate of the motor is 1.42 into 10 to the power of minus 3. Substitute these two and simplify this, we will get theoretical flow rate for the motor is 1.332 into 10 to the power of minus 3 meter cube per second. And QT motor means theoretical discharge for motor equal to Vd into N. This is the main thing. Vd is unknown, right? For in case of motor, volumetric displacement for motor is unknown. We have to find out this one with the help of this QT motor, and N is given as a data. Substitute both values, we will get easily. Here Vd motor is unknown. Vd motor equal to Qt motor dividing Qt motor into 60 dividing by speed, that is 1.332 into 10 to the power of minus 3 into 60 dividing by 600. 600 is the speed. Simplify this, we will get 1.332 into 10 to the power of minus 4 or 133 centimeter cube per revolution. The subquestion A, that is displacement of motor, displacement of motor is 133 centimeter cube per revolution. Next subquestion B is theoretical torque delivered by motor. Here there is a formula, theoretical torque equal to pressure into volumetric displacement dividing by 2 pi in case of motor. Here P is 105 into 10 to the power of 5 into 1.332 into 10 to the power of minus 4 dividing by 2 pi. Simplify this, we will get 222.818 Newton meter. Here we got theoretical torque. Now we will move on to mechanical efficiency of the motor, that is nothing but a actual torque dividing by theoretical torque. Theoretical torque answer just we got, it is in our hand. Just substitute the values. Mechanical efficiency also given as a data, that is 92%. So 0.92 equal to TA is unknown, dividing by TT, that is 222.818. Simplify this, we will get actual torque for the motor is 205 Newton meter. So the sub question B, the actual torque for the motor is 205 Newton meter. Thank you.